For first introduction, what is maximum and minimum problems? Many application problems in calculus involve functions for which you want to find maximum or minimum values. The restrictions stated or implied for such functions will determine the domain from which you must work. The function, together with its domain, will suggest which technique is appropriate to use in determining a maximum or minimum value, such as the extreme value theorem, the first derivative test, or the second derivative test. So why we use maximum and minimum problems is maximum and minimum problems are used to optimize real-world outcomes such as minimizing the surface area while keeping the volume constant. By applying differentiation and finding the critical points of the surface area function, we can determine the optimal dimensions of the container that achieves these objectives. This process illustrates how optimization using calculus is crucial in various industries for designing efficient and cost-effective solutions. So there are example for selected formula to find surface area.
So for my first question is that I need to show that the surface area of the rectangular box is given, which is area is equals to 2x squared plus 864 over x. The first step I do is to use the general formula for the rectangular shape, which is 2 times length times width plus length times height plus width times height. Once I know the formula that is needed, I substitute the given information into the formula, which is y as the height, x as the width, and 2x as the length. I undergo some expansion and then I got the answer, which is shown. For my question is that I need to show that the surface area of the rectangular box is area is equals to 2x squared plus 864 over x. In order to do that, I need to identify its general formula for the surface area of rectangle, which is 2 times length times width plus length plus height plus width plus height. It is given that the height is y centimeter, the width is x centimeter, and the length is 2x centimeter. Then I substitute the given information into the surface general formula for surface area for rectangle. I undergo some expanding to reach the like term, and then for the last one, and I finally shown that the surface area of the triangle is the same as the question given, which is the area is equals to 2x squared plus 864 over x.
In question 2a, we express the height of the cylinder in terms of the radius, using the total volume of the container, which is 45 pi, to derive the formula, which is h equal to 45 per r square minus 2r per 3. In question 2b, we calculate the total surface area of the container by combining the contribution from the encircular part, the hemispherical lid, and the circular base. The curved surface area of the cylinder is 2 pi r h. The curved surface area of the hemisphere is 2 pi r square, and the area of the circular base is pi r square. Adding these together, we get A equal to 2 pi r h plus 3 pi r square. Substituting the expression for h derived in part A, which is h equal to 45 per r square minus 2r per 3 into the formula, we simplify the terms to show that the total surface area of the container is indeed A equal to 5 per 3 pi r square plus 90 pi per r. In question 2c, we determine the radius of the cylinder when the total surface area is minimized. Starting with the surface area formula, A equal to 5 per 3 pi r square plus 90 pi per r, we differentiate A with respect to r and set the derivative equal to 0, solving 10 per 3 pi r minus 90 pi per r square equal to 0. We find 10 r cubed equal to 270, which gives r equal to 3. To continue, D is minimized. We calculate the second derivative and verify it is positive at r equal to 3, ensuring that the surface area is minimized. Therefore, the radius of the cylinder is r equal to 3 cm.
So the conclusion that we get from maximum and minimum problems is first, optimal solutions. This problem help identify the optimal values, maximum or minimum of a function, which is often essential in real-world application like minimizing cost, maximizing profits, or optimizing physical dimensions. Second, critical points analysis. By finding critical points where the derivative equals 0 or is undefined, and analyzing their nature using the second derivative or other techniques, we can determine whether the function is increasing, decreasing, or at an extremum.